it is based on tutorial question 22, and we have to address the issue when the set of vectors of this structure, or when the set of vectors of this structure is a subspace. Actually, we have to prove that this is a subspace. So look what happens here. We take the collection of all vectors in two-dimensional space, which are a result of multiplication of the fixed given matrix A by a vector in 3 dimensions. Here's my matrix A. That's the matrix which is in question. It's a 2 times 3 matrix, 2 rows, 3 columns. Here's the components: 2, -3, 1, 4, 5, -3. So again, we're looking at the set of vectors which are the results of this sort of matrix multiplication. We multiply this matrix by the column vector of size 3. There will be something as a result of such multiplication. We collect all of this something, and this collectively, this is a set. We would like to prove that this is a subspace. You can do it directly if you wish. In principle, this can be done directly via subspace theorem. But my job today, my objective today, is to connect everything with the second category of the subspaces, span subspaces. And I will show you how to connect this with a span subspace. It's a very nice method, and it's highly advisable that you remember this connection between this type of construction and span subspaces. So look what I'm going to do. I'm going to look at this. So I take a vector B from this S. Here's what I just said to you verbally. Here's the writing of this. Vector B in this subset S. You see, I'm using the term subset because we haven't proved that it is subspace yet, but we will in a second. It will be in a subset if you can find a vector X, that's my column vector of dimension 3 in R3, such that B is the multiplication by this column vector X of the matrix A. Basically, this is just interpretation of what is said here. I just replaced this for sum with this fancy symbol, which we read exists, or for sum, and I replaced X with the actual components of X. Otherwise, it's identical line to what is said here. But now, because I have the names for the components of the vector X, I can actually write out this multiplication. We know how to multiply a matrix by another matrix, or matrix by a column, right? We take this first row and dot product this first row with this column. And that will be the first component of the result. Then we take the second row and dot product this with this column again, and it will be the second component. Here's the result of it. Look at this. First component of my multiplication is the dot product of this vector 2, -3, 1 with this column. Double x1, take 3x2 plus x3. Second component, another dot product, this vector with this column. That's a second component, 4x1, 5x2, take 3x3. So now we have very explicit form of the elements of my S. Every B from S, it is of this structure. Now I'm going to rearrange the structure. Look at what I'm going to do. What I'm going to do. I'm going to split this. I'm going to split this vector. It's a vector with 2 components. First component, second component. I will split this vector into the sum of individual numerical vectors. Look at this. Vector next to the x1 component, it's the vector with the coordinate 2 and 4. No more x1 present here. x2 comes with this vector, -3 and 5. There is no more x2 presence. x3, it comes with this vector. With this vector, yes, vector 1 and -3 components of that vector. So that's how I can rewrite my B vector. And that is exactly the linear combination, isn't it? That is the linear combination of these 3 vectors. This, and this. So what we have proved with you just now, right in front of you, I have proved that the vector B in my S, if and only if my B falls into the span of these 3 vectors. 2, 4, -3, 5, and 1, -3. Or effectively, I can just say that this S which was originally constructed in a different way. It was originally constructed as a result of, as a collection of all vectors, which are the result of multiplication of three-dimensional vector by the fixed matrix A. This S is a span of these three vectors. And the connection of my vectors to my original matrix A, these are the vector columns of my matrix A. And because we know from the previous slide that the span is a subspace, S is also a subspace. By reference to the span lemma, S is a subspace. You see, I'm not using the subspace theorem directly. I'm making the reference to the previously established result. By connecting my new S, by showing the span structure in my new S.